So this video will be on using L'Hopital's rule to solve limits. So we're going to kind of go back to limits now. And this thing called L'Hopital's, and often it's people put an S in here, like I think our book does, and so this looks like hospitals, and that's what we used to call it. But I think the correct French pronunciation is this French guy, and people say L'Hopital's now, so that's what I'll try to say, not L hospitals. Okay, so L'Hopital's rule to solve limits. So let's review limits here. So if you remember in limits, there are the ones that we don't know the answers to that are the hard ones. Okay, we have to do work, are when we get 0 over 0, and like, okay, which one wins? We have to do some work here. We get infinity over infinity, or plus or minus infinity, whatever, but we get infinities over infinities, we got to do work. If we get infinity minus infinity, we have some function minus another function, they both go to infinity, which one wins? Does this one bigger? Sometimes this is equal to 2 or something. We don't know, we got to do some algebra. Or if we have like 0 times infinity, so one function goes to 0, one goes to infinity, which one wins? I think these are the 4 that we don't know. Can't think that's it. Now the ones we do know, right, if we have something like 0 over infinity, well that's definitely 0, right? That's like super 0, because 1 over, that's the same thing as like any number, like 3 over infinity. That's also 0, because it's like an infinitely big fraction in the bottom here. Okay, so those we know. Or if we have infinity over 0, that's like super infinity, which is the same thing as like 3 over 0. Anything over 0, a solid number over 0, including infinity over 0, is going to be infinity. That's all fine. Now sometimes we got to be careful, is it positive or negative infinity? You know, we got to play those games. As you go to positive, negative infinity, we're going from the left, from the right, all that kind of stuff. Clearly infinity plus infinity is 0, or says 0 is infinity, or infinity times infinity is infinity, infinity is infinity squared, whatever that means. Okay, so those are things that we know the answers to. The only tricky ones, well, of course, 0 over infinity, I always said that 0 over 3 is, of course, 0, you know. The only tricky ones are these. These are the ones we don't know the answer to. So you plug in your numbers, you get this, you're like, okay, got to do some work. So, and if you remember, some of our techniques that we used, and I hope I can remember them all. The first thing we talked about is we could factor. You know, you factor them out if they're quadratics and stuff, you can factor them and cancel, so you don't get 0 over 0 on the bottom. So you get one of the things like 0 over 0, you factor it, cancel it out, then you can plug in the numbers. We also did the conjugate ones, which tend to be a lot of work. You got to multiply by the conjugate, top and the bottom by the conjugate. We did common denominators, which are for the fraction ones, and those are a lot of work too. You got to find the common denominators, add fractions, do all that kind of stuff. That can be we divided by the biggest power of x. If they both go to infinity, you can divide by the biggest power of x. We did those, and that can often help out. Biggest power of x. Sometimes you got to do a couple of these, like we did conjugates and then divided by the biggest power of x. There's this thing called the squeeze theorem that we played with a little bit. It's kind of tricky, but it's kind of cool. Let's say if this function goes to 0 and the other one goes to 0, then the one that you have must go to 0 too. You squeeze it in between two functions that you know about. It's kind of like waving your hands and making this argument. It's kind of weird, but okay. So that's what we have so far. So what we're going to learn now is this guy named L'Hopital, this French guy, figured out, he proved it, and we're not going to prove it because I have no idea how, and it's supposedly pretty complicated, but it's mathematically true. He said, this is a really cool thing. So this is a brand new technique, which is really easy. It's actually a really cool thing because it's easy. So you're using L'Hopital's rule, and it says that if you get a limit, and if you get 0 over 0, or infinity over infinity, and it can be plus or minus infinity over plus or minus infinity, if your limit's equal to that, then what you can do is it's the same thing then is equal to, you can take the derivative of the one on the top and the derivative, I'll make it a different function, of the one on the bottom. Now of course this only works if you have a limit that's a fraction. So if you have a function on the top and a function on the bottom, you can take their derivatives and find the limit of the derivatives in the top and the bottom. And that will be the same thing. You'll get the same limit. So but it has to be 0 of 0, infinity, infinity. It can't be infinity minus infinity or 0 times infinity or something. You have to write it as a fraction. So if you can write a limit as a fraction, then you can take the derivative of the top and the derivative of the bottom. Remember, it's not, and it was a cool thing, it's not quotient rule. It's not the derivative of the whole thing. That's a lot of work, right? The quotient rule. It's the derivative of the top, derivative of the bottom. And that's the same thing. And it kind of makes sense because what you're doing is seeing how fast they change, right? The derivative is how fast things change. So you're seeing, does the one on the top change faster or the one on the bottom change faster? And depending on which one changes faster, it could give you the answer for the limit. Now, and here's the other cool thing. If it doesn't work the first time, you can take the derivative again. Take it twice. Take the derivative of the derivative, second derivative of the top and the bottom, and then do it again until you get something that works. Sometimes it never works and you can't use L'Hopital's rule, and sometimes you got to take the derivative 5 times and then finally it'll work. Okay, so let's do some examples because that's how you do these things, to show you how cool this is. Okay, so let's do the example of, let's say we have the limit as x approaches 1 of ln of x divided by x minus 1. Okay, so here's on the final, you have this question, oh my gosh, how do I do this? I can't factor ln of x. And okay, first of course we plug in 1. And ln of 1, we plug in 1. What is the ln of 1? And we get here that ln of 1, in other words, okay, when you say ln, that means e to what power is equal to 1, and we know that e to the 0 is equal to 1. So ln of 1 is equal to 0. Okay, and you plug in ln of 1, you calculate, you should get 0, because e to the 0 is equal to 1. And we plug in 1 in the bottom, we also get 0. So here we get 0 over 0, because plug in 1, which means we can use L'Hopital's rule, because what else can we do? We can't factor this, or biggest power of x. There's no other way to do it. So let's use L'Hopital rule. We take the derivative of the top and the derivative of the bottom. It's real easy derivatives, right? So this is the same thing as the limit as x approaches 1 of the derivative of ln of x is just 1 over x. So we have 1 over x in the top divided by the derivative of x minus 1. Well, the derivative of minus 1 is 0. That's just 1. Well, okay, now let's plug in 1 here. So that's just 1 over 1 divided by 1, which is clearly 1. So the answer is 1. So if we plug this in Desmos, as x goes to 1, this quantity here goes to 1. How easy is that? Isn't that awesome? Let's do another one that actually we did before, and it was really tricky to do when we worked it out in the book and, kind of stuff. So let's do this one. Limit as x approaches 0 of sine x over x. I think before we had to use the squeeze theorem, and it's kind of tricky. So let's see, remember, so plug in 0 first. Sine of 0 is 0. X, of course, that's 0. We get 0 over 0. Right? So what do you do? So let's use L'Hopital's rule, because again, L'Hopital's rule works for 0 over 0 or infinity over infinity. So take the derivative of the top. Derivative of the top is cosine of x. Derivative of the bottom is 1. Now let's plug 0 in. Cosine of 0 is equal to 1. So that's 1 over 1, which is 1. So this limit is equal to 1. Super easy, right? It's unfortunately not always so easy, but oftentimes it is this easy. What looks like an impossible thing, like wave your hands, what do you do now, actually works out pretty good. Okay, let's do another one. Let's say we have e dx over x squared. Let's do an infinity one. So limit as x goes to infinity of e dx over x squared. Again, our old methods, how do we know what works, right? Which one goes infinity fastest? Obviously we get infinity over infinity. So we can use L'Hopital's rule, but there's no other way we could have done this before. Like, can't factor it and cancel things out and stuff. But now we can use L'Hopital's rule. The derivative of e dx is e dx. Derivative of x squared is 2x. Still we get infinity over infinity. It's a bit smaller infinity in the bottom. It's not x squared, it's 2x, but it's still infinity. So here's a really cool thing. We take L'Hopital's rule again. We take the derivative again. Derivative of the x, we get e to the x again. Derivative of 2x is 2. Now, clearly, this goes to infinity because we have, now you plug in infinity, we finally get e to the infinity over 2. We get half of infinity, but that's still infinity. So the answer is infinity. So we had an infinity over infinity, and we know the answer now is infinity. It actually does go to infinity. So, and that's okay. So that's our answer. Let's do another one since these are so fun. Let's say we have ln of x over x cube root of x. And these, I'm just taking these from the book's examples. So, because they're nice examples. So let's say limit as x goes to infinity. Yeah. Okay, ln of infinity is infinity. Cube root of x is infinity. So the question is, which one goes there faster? Does the top win or the bottom win? That's what the derivative can tell you. So we have infinity over infinity. We can't do any of our own old techniques, but we can take the derivative. Derivative of ln of x is 1 over x. Derivative of cube root of x, let's rewrite that as x to the 1/3. So we have 1/3 x to the, let's see, take away 1 negative 2/3. Okay, that's kind of confusing. So let's rewrite this. X to the negative 2/3 in the bottom is like x to the 2/3 in the top. And dividing by 1/3 is like multiplying by 3. Or let's say we multiply top and bottom by 3, cancels out. So that's equal to 3 over x, that's what's in the top here, right? Multiplied by 3, times x to the negative 2/3 in the bottom is like x to the 2/3 on the top. Okay, well that's x to the negative 1. So we can write that as 3x to the negative 1 times x to the 2/3. Let's see, that's the same thing as 3 times minus 1 2/3. That's negative 1/3, right? Negative 1 plus 2/3 is negative 3x to the negative 1/3. Now let's rewrite that as 3 over, there's probably a faster way to do this, but this isn't hard, x to the 1/3 power. Okay, let's plug in infinity now. 3 over the cube root of infinity is infinity. So that's like 3 over infinity, which is clearly 0. So this limit is equal to 0. So there's maybe an easier way to do this algebra, but still, the basic thing is it's not very hard. Just got to be careful with negative exponents on the bottom, means positive on the top, stuff like that. And we can get that's equal to 0. Okay, let's do another one. This is a really cool one. They do this one in the book too, but I'm going to do it here because it's cool. Oops, I've been writing example every time. I don't want to break my pattern here. Example. So let's say we have limit as x approaches 0 of x ln of x. Now, to review, if we can't have the natural log of a negative number, because that's like saying e to what power gives us a negative number. And e to a power, you can't make this negative no matter what x is. If we can't make this negative. If we make it e to the negative infinity, that's just the same thing as 1 over e to the infinity, which is 0. So the natural log of 0 is negative infinity, but we can't make it negative. So ln, we can't have a negative x here. So we have to say approaches 0 from the positive side. If I didn't have that positive there, we'd say it does not exist, because from the negative side it doesn't exist. From the positive side we have an answer. So you would say d and e and be done, but that's too easy. So we're going to put it from the positive side, so x is always positive. As we go smaller and smaller, what happens? Well, ln of 0 is negative infinity. So to show, because e to the negative infinity is equal to 0. And this is 0. So here we have a 0 times negative infinity. That's one of the ones we don't know the answer to. Which one wins, the 0 or the negative infinity? So we got to do some work. What do we do? There's no factoring or anything. And this is not a fraction, but we can write it as a fraction. So that's, sometimes you got to do that. You got to make it into a fraction, force it into a fraction. So this is the same thing as the limit as x approaches 0 from the positive side of ln of x divided by 1 over x. You know, it's kind of weird, but it works. So x is the same thing as 1 over x, right? X in the bottom of the bottom is like x in the top. We multiply the bottom by x, top by x, these cancel, we get back that. Okay, now we can use L'Hopital's rule because we have a fraction. And because we have now infinity over infinity. If we have 0 in the bottom here, 1 over 0 is infinity, and ln of 0 is over infinity. So we have infinity over infinity now, so we can use L'Hopital's rule. That's the thing. You got to be careful of that. You have to get infinity or 0 over 0. Okay, so now we can use L'Hopital's rule. So what's the derivative of ln of x? We get 1 over x. This is x to the negative 1, right? So the derivative of x to the negative 1 is negative 1 x to the negative 2. Okay, let's rewrite that. It's negative, and x to the negative 2 in the bottom is like x squared in the top. So this is the same thing as negative 1 over x times x squared. So let's see. So that's just x squared cancels out the x. So that's just negative x. So now we can plug in x equals 0 and nothing bad happens. And so we get 0. We get negative 0, but negative 0 is still 0. So the answer is 0. So the 0 wins. So this thing goes to 0 faster than it goes to infinity. This one goes to infinity, this one goes to 0. The 0 wins here, so we get 0. So again, this is a case where we got to force it into L'Hopital's rule. We got to make it into a fraction, so we get infinity over infinity, and we get that. Okay, one more example. Again, this is so much fun. Let's say we have the limit as x goes to 0 of x to the x. Okay, let's see. That's kind of cool, right? So what happens? So what is, in other words, what is 0 to the 0 power? The general rule is anything to the 0 power is 1, right? So x to the 0, anything to the 0 power is 1. But what about 0 to the 0 power? Is that 1? 0 should be 0, no matter what's up here, right? 0 is 0. So what's the answer? As we get closer and closer to 0, what does this thing do? What does it approach? And what does it actually equal? And if you put it in on Desmos, you'll see it actually equals something. So what is 0 to the 0? So we can use our rules now to figure this out. Okay, and we have to come, I think, from the positive side. X approaches 0 from the positive side. Okay, so let's figure this out. We can't use L'Hopital's rule. It's x to the x. Like, what the heck? However, here's the cool thing. We can do our e to the ln trick. Because this is the same thing as e to the ln of x to the x. Right? This is our logarithmic differentiation, so this is like logarithmic limits. So if you write it like that, that's the same thing. Remember ln, the reason we do that is because this x comes in front. That's the same thing as e to the x ln of x. So in a sense we're saying what is the limit as x approaches 0 of e to the x ln of x. Well, what we're really doing here then is what we're seeing is what happens when this approaches 0. So what we got to do is see what happens when this approaches 0, and then we can later raise it to the e power. So in a sense what we're saying is first we figure out the limit as x approaches 0 of x ln of x. But we already did that. That's the one I just did. Right? The limit of x approaches 0 of x ln of x is 0. So, and remember I said it had to come from the positive side, and that's why I said from the positive side here. So from the positive side, we already showed that's equal to 0. So this thing here, as the limit of x approaches 0 from the positive side, is e to the 0. Since that's 0, which is 1. So we just proved that 0 to the 0 power is equal to 1, which is kind of crazy. But that's how you do it, using limits. So again, the trick was here, we can't use L'Hopital's rule directly, but we can use our logarithmic thing, and then we can just do what's up here, the x ln of x, which we already did in the last example. We know that's equal to 0, so we get e to the 0, which is equal to 1. Kind of cool. Okay, that's just reviewing limits and this new technique using L'Hopital's rule, which is actually makes life a lot easier. And I'll give you some examples, some things for you to work out on your own for how to do these. Thanks for listening.